Welcome to the course module of Communication Engineering. And in this video, we are going to solve another GATE problem, which was asked in GATE 2022. Okay. So here you can see this problem. Okay. So this problem, if you read this statement of the problem, it is mentioned as a circuit with an ideal op-amp shown. The word plot of the magnitude in dB of the gain transfer function AV, which is defined as V output divided by V input of the circuit, is also provided. Okay. Here omega is the angular frequency in radians per second, and we have to find out the values of R and C. So here you can see this is the op-amp circuit, which is shown here in the picture. Okay. And here it is, its board plot is given. So this board plot is nothing but the frequency response of this particular filter is given, right? So though it looks like this problem belongs to analog circuits, okay, but those who have already watched my video in communication lab, in which I have described you about how to obtain the frequency response of a low pass filter, they can easily crack this problem from that explanation. Okay, so it is requested to the viewers, please follow that particular lecture, and whatever the concept I have already discussed in that particular lecture, you try to solve this particular circuit based on that concept. So please you pause this video for 2 minutes and try to solve that particular this particular problem by following that concept that I have already discussed. Okay, so that was the experimental part. While doing the experiment of second order or first order low pass filter, I have already discussed this particular concept. Okay, so you can comment your answer, okay, your options, that whatever you are getting. So now I will try to solve that this particular problem, okay, based on whatever I have explained in my first order low pass filter design. So here you can see this is nothing but your low pass filter, because we are having RC circuit. Okay, and here we have this two resistances value, which will be giving you a certain gain to this particular low pass filter, right? So because it is a low pass filter, here you can see its frequency response, which is also mentioned here, right? So here we have the frequency component onto the x-axis, and here we have the gain of this filter, okay, gain of this filter onto the y-axis, which is mentioned in the dB. Okay, so here we can see because we have to find out this capacitance value C, and we have to also find out this resistance value R. Okay, so how to find out these values, that we can see here. So first of all, if you see from this board plot or frequency response curve, its maximum gain is being defined as 12, okay, 12 dB, right? So this particular gain is defined in dB, right? So it is 12 dB. So here we can, from the plot itself, we can see this gain is actually reduced by 3 dB at frequency log 10 omega equals to 3. Okay, so at log 10 omega equals to 3, this gain is reduced by 3 dB. So therefore, this frequency at omega equals to omega c, this log 10 omega c will become means your 3 dB cutoff frequency of this particular filter, right? So that we can make a substitution over here, and then we can try to solve it. So before that, you see in this circuit, there are two resistances, 1 kilo ohm and 1 kilo ohm is connected over here. So I will give this resistance name as R1. Okay, so I will first define this resistance as R1, and then I will solve this entire problem with this R1, and then at the end I will substitute R1 equals to 1 kilo ohm, right? So first of all, what we can see is from the 3 dB from this particular board plot, we can write this 3 dB cutoff frequency, and that 3 dB cutoff frequency we can write as log 10 omega c equals to 3, because here you can see at this particular frequency, this gain has reduced by 3 dB, and initially it was 12 dB and now it has become 9 dB. Okay, so therefore it will be your 3 dB cutoff frequency. So log 10 omega c you can write equals to 3. Okay, so here we can get this value of omega c this will be equals to 10 to the power 3, right? So in normally in any low pass filter, okay, if it is a first order low pass filter, then the 3 dB cutoff frequency of the low pass filter, omega c will be defined by this particular expression, omega c equals to 1 upon R1 into C, right? So this is the formula for calculating the 3 dB cutoff frequency, right? So here this R1 means I'm talking about this particular resistance, right? So here this particular resistance R1 multiplied with the capacitance C. So this ratio 1 upon R1 by 1 by R1 into C will give you a 3 dB cutoff frequency in radians per second, right? So here we can substitute the value of omega C, okay, and the value of R1, right? So if you substitute that, you will be able to calculate this value capacitance. This capacitance value will be 10 to the power minus 6, or you can write this value is equals to 1 microfarad. So it is very simple to calculate from this given data, right? Similarly, if we wish to calculate the value of resistance, this resistance, right? So calculating this resistance, we have to use the another information given in this particular graph, okay? So that information is about the 3 dB, about the gain in dB, right? So this is the gain mentioned over here. So first of all, we have to calculate what is the transfer function of this entire circuit, and from there we have to calculate this gain AV, right? So we have to calculate this particular, we have to exactly we have to get the this expression of your AV, right? So that we have to calculate. So to calculate that, we can first apply the Laplace transform. Okay, so because this is resistance R1, its Laplace transform will remain R1, and for capacitance, it will be 1 by SC. So here we can apply the Laplace transform and we can find out what is the potential V plus S. Okay, it means we have to calculate the potential at this non-inverting terminal, so that you can easily calculate. Okay, so this value will be given by this particular expression, V plus S equals to V input S divided by 1 plus R1 CS. Okay, and due to the concept of virtual circuit, this V plus will be equals to V minus. Okay, so because this is non-inverting, this is your non-inverting terminal, this is your inverting terminal, so these two potential will be equal, right? So now you can again apply the nodal, you can apply here KCL at this particular node, okay? And then you can correlate the relation between V output S and V input S. So if you do that, this simple calculation, right, this expression we can write here, and then this can be modified to get this particular expression, V output S divided by V input S. This will be equals to R1 plus R divided by R1, 1 plus R1 CS. So this will be the expression, right? This will be the expression. So here we are getting this particular expression, and this expression we will be calling as the gain of this low pass filter, and which is defined as AV, right? So now we have to look at this given data in the graph. So what data it is given here, that we can see when this log 10 omega is equals to 0, right? So at log 10 omega equals to 0, it means that omega is equals to 1. So that we can see. So at log 10 omega equals to 0, this omega will be equals to 1. So at omega equals to 1, this gain in dB is defined as equals to 12. Okay, so its value is 12 from this graph, right? So that we can write at omega equals to 1, gain in dB is 20 log mod of AB is equals to 12. Okay, because this value is given in dB, right? So that's why we have to write 20 log 10 mod of AB equals to 12. So if you solve this particular expression, you will be able to show that this mod of AV is equals to 3.98. So what we can have is that at omega equals to 1, this value is 3.98. So because it is a low pass filter, we can consider that at omega equals to 0, this value will be almost equals to 4. Okay, so it is almost equals to 4. So one thing that we can do is, if you want to exactly calculate the value of R, okay, what you can do is you can calculate the mod of this particular expression. And here you have to substitute S equals to j omega, and then you have to calculate the mod of this particular expression, right? So here that mod will be R1 plus R divided by R1, and here it will become root over 1 plus, you have to substitute here j omega, so it will become R1 square C square omega square, okay? And then you have to substitute mod AV equals to 3.98, and here you have to substitute omega equals to 1 to exactly get the value of this R, okay? So, but here what we can do is we can approximately calculate the value of R to get our answer, okay? So what I will do is, because at mod omega equals to 1, this mod of AV is equals to 3.98, what we can assume is that at omega equals to 0, this value will not have a much different value, okay? So we can assume that this value will be approximately equals to 4, okay? So it may be assumed, because it is a low pass filter, so it can be assumed almost equals to 4. So this will simplifies the calculation over here. You can see that if we substitute omega equals to 0 in this particular expression, this term will actually eliminate it, right? So if this term will eliminate it, if you take the mod, we will be only left with this particular ratio R1 plus R divided by R1, okay? So here we can write this particular ratio R1 plus R divided by R1. So this value will be equals to 4. And if you solve this expression further, and if you substitute the value of R1 equals to 1 kilo ohm, then this value of R that we can get is 3 kilo ohm. So please make this correction. Here we have to calculate the value of R, okay? So here I have made, you have wrongly written R1, it is value of R, okay? So this R will be equals to 3 kilo ohm. So now you can see which particular option is suitable, okay? So here you can see the value of R1, R is equals to 3 kilo ohm, and the value of capacitance is 1 microfarad. So here you can see this option A is having this combination, okay? R is equals to 3 kilo ohm and C equals to 1 microfarad. So I hope you must be able to understand, okay? So those who have not watched this particular video about the low pass filter, okay, the experiment that we did, okay, I will share the link in the description box. Please go through that video so that you will have the better understanding of this particular problem. Thank you for watching this video. If you have any query, let me know with your comments. Thank you.